Hello everyone and welcome to this video about Taylor expansion. This is actually also already the last video in our course, and we continue exploring some baryon-dense applications. Basically what we have been discussing in these last two videos are two methods that can be used in order to circumvent the sign problem in regions where it is not so severe, and then one can circumvent it based on using methods that are based on standard Monte Carlo simulations run at zero chemical potential in this case. And as we said in the previous video, this allows us to at least explore the hotter and diluter QCD states in this sketch of the phase diagram. And in particular, one can look at interesting things. So not going into thermodynamics and limiting ourselves to the study of the phase diagram itself and its boundaries or regions between phases. One interesting thing that we can look at is, how does this curve bend and whether at some point there is a critical endpoint. And here we are with Taylor expansion method, which is based on an expansion of the partition function in a parameter which must be small, that is the quark chemical potential over T. And then what we do is we learn about non-zero quark chemical potential from ensembles that are generated at zero chemical potentials, of course, in that case, using standard Monte Carlo techniques because they are doable there. All right, now Z is analytic everywhere, at least for as long as we will simulate it on a finite volume, and that's all we can do. And this we know because it is expected on the basis of Li-Yang theory. Then what one can do is one can take the pressure, which is the volume divided, the logarithm of Z divided by the volume multiplied by the temperature, and consider even powers only, thanks to the fact that we can use charge conjugation invariants. And then one has the leading coefficient, that is the pressure at mu q equals 0, which is directly, in a sense, measurable, as we discussed in the video about the equation of state in QCD. Directly meaning that one can employ standard Monte Carlo techniques based on importance sampling. Indirectly, in the sense that you still have to do the integral method to obtain the pressure, but it is nevertheless something that is not sign problem affected. And then higher order coefficients are derivatives of the pressure, and they are themselves evaluated at mu q equals 0 in the Taylor expansion. And therefore, this we can also calculate based on mu q equals 0 ensembles. Then what are the pros and cons of the Taylor expansion? Like we discussed previously about the reweighting. It is very good that it is a computationally well-defined strategy, and that the series for other thermodynamic quantities will naturally follow by the one for the pressure. So if you are able to construct the expansion for the pressure, then in principle you can obtain from there all other thermodynamic quantities. However, what makes it pretty tough to implement and to sort of bring the results to a decent degree of precision and accuracy is the fact that higher order derivatives are very complex and complicated to measure. And full functions are only well approximated if there is a rapid convergence in mu q over t, such that the entire series, which in principle contains infinitely many terms, is dominated by the first few. And then we see how that works in practice. So one can write down a delta of the pressure, so that basically the leading order term, which is a constant, is brought on the left-hand side. And then one is left with these even powers of mu b or mu q. As you know, they are connected by a factor of 3 by now, you know it. And the corresponding second, fourth, sixth, and so on derivatives, okay? So in general, one can write it down in a compact form in this way, where you basically can identify what is the definition of this. Sorry, I can't select the numerator of this chi b to n, where 2n stands for the fact that you only have even power and b stands for baryon, because we will see other susceptibilities in a moment. Now, remembering the expression for the partition function, in the case in which we have an F-degenerate fermion species, as you can see from the corresponding power of the fermion determinant after having integrated out the fermions as Grassmann variables, one can take one more step and bring the determinant at the exponent, and then one needs to be able to take derivatives, and in particular derivatives of this form, where you take derivatives of the logarithm of z against mu b, which then gives the expectation value of this quantity, where you are left with taking derivative of the logarithm of the partition function. That's the only place where you have a mu b dependence in this form for the partition function. And then also the second derivative, which already takes a more complicated and much less compact form that you can easily work out, and so on and so forth with the higher order derivatives. And in taking the mu b derivatives of the logarithm of the determinant, one can also make use of this relationship, connecting the logarithm of the determinant to the trace of the logarithm. And this leads to expressions that can be written in terms of the quantities that I have worked out and written down in the slide. So linear derivative and second derivative, they contain expressions such as the trace of the Dirac operator inverse and derivative of the Dirac operator against mu b. In the other case, you have either a second derivative in the first term, or you have one more time multiplied the inverse of the Dirac operator in the subsequent term. And you can imagine that these expressions get more and more complicated the higher the order. Not only, but they involve inverses of the Dirac operator and traces and so on, so they are pretty tough to calculate with a good degree of accuracy and precision, and therefore here are the pros and cons of the Taylor expansion revisited, now that we have sort of looked into how it works when you have to work out the formula. And the good thing is that, okay, you have derivatives of d slash as a function of mu b, but these are at least local operators. And what one thing we can do is we can calculate them using random noise vectors techniques. Actually, this reminds you a lot about the chiral condensate, probably. And I mentioned in one of our class that this is the kind of technique that you use in measuring the chiral condensate. Even though I didn't enter into details, I just told you what that is called like. Okay, that higher order derivatives are very complex, I already said, and this is certainly a cons. The number of terms in particular increases rapidly. You will work it out in the assignment as well. And rather sophisticated techniques are needed in order to increase the accuracy and precision of the calculation. One can apply the Taylor expansion method to what we call the conserved charge fluctuations. So in our attempt to locate the critical boundaries or endpoints in the QCD phase diagram, we know that thermodynamic quantities largely fluctuate near critical points. This is just a property of close to the critical points of the correlation length that diverges, and therefore the fluctuations get larger and larger themselves. And if we think about the actual experimental physical application, it happens that most of these critical fluctuations that are the footprint that there has been a transition are unfortunately washed out in the, unfortunately, well, that's how it happens, in the expanding and cooling medium after the heavy ion collision has taken place. So how do we go about understanding from the decay products after the medium has cooled down and rehadronized that there has been phase transition? one can look at fluctuation of conserved charges because as they are conserved, they basically freeze out at a temperature, at a given temperature and chemical potential, which is called, indicated by this FO superscript. And so this is when these fluctuations are frozen and then survive till the end. Okay, so if we look into quantities that are conserved from freeze out on, then what we see as memory of what has happened at freeze out. So this is the idea. We probe the thermodynamic conditions that are created in heavy ion collisions much before we can detect decay products in the detectors. And we do that via the analysis of event-by-event fluctuations of those quantities that we know are conserved afterwards. In particular, baryon number, electric charge, and strangeness, and their higher order cumulants as well. So we get the full information on their distribution. All right, and then whether we are sensitive or not to the critical endpoint depends on how close these coordinates of chemical potential and temperature at freeze out are to the actual critical endpoint. But the critical endpoint is expected at small mu b, so yes. On that depends the sensitivity of our method. And one can look, as I wrote up here, also to higher order cumulants of these event by event fluctuations. And these are what we call key NB. N is the order, and B stands for baryon. These are susceptibilities of the net baryon number fluctuations, and they are derivatives of the pressure over T to the power of 4 at mu b equals 0. So you very soon identify them with the coefficients of our Taylor expansion the way we have discussed it until now. So they can be calculated, sorry, I'm missing a space here, by Taylor series expansion at small mu b over T. Okay, so here is the connection. And this is what makes it interesting to look at these susceptibilities, which are also the coefficients in the Taylor expansion. All right, and they are defined according to the formula. As you see, they're evaluated at mu b equals 0, which is why we can measure them with ordinary standard Monte Carlo simulations. Okay, this kind of strategy has been adopted in the literature in many, many studies. I'm just quoting an example over here. The nice thing is that to leading order, one gets complementary information on the location of the freeze out in the direction of the baryon chemical potential and in the direction of the temperature. So one can pinpoint this point in the phase diagram. Ratios of even and odd cumulants that can be constructed in this way. So you measure them separately and you compute the ratio, event by event or configuration by configuration in our case. And one can determine, I mean, this gives information on the ratio of the temperature over chemical potential at freeze out. On the other hand, if one looks at the ratios of even cumulants, this apparently is only sensitive to the temperature of freeze out. So altogether, you get the full picture and the full information. Yes, and you can see some examples in here of these ratios and M, and B stands for baryon. And you can see that they are also directly sort of compared with the experiment, because the advantage is that these quantities are can be measured in event by event fluctuations by experimentalists as well. So let's summarize what we said, or what is the main idea. What we do is a phenomenology-aware Taylor expansion method based on the fact that conserved charge fluctuations in heavy ion collisions reflect the thermodynamic conditions of the expanding medium as soon as it gets cold and dilute so as to rehadronize. Then we also know that hadron resonance gas model is doing a good job in approximating the partition function below in the hadronic phase by that of non-interacting gas of hadron resonances. Baryon number fluctuations and hadronization happen to be both well described by statistical hadronization models that are based just on this hadron resonance gas model. And the medium at freeze out is described by the thermodynamics at that set of coordinates in the phase diagram that I mentioned before one can get out of studies of ratios of susceptibilities that can obtain in this method. So the plan is to extract freeze-out parameter by comparing experimental data with lattice QCD. And this will teach us something about the thermodynamic properties of the medium at freeze-out, okay? Then the actual strategy to extract the freeze-out parameters is that one can use fluctuations of conserved charges and their higher order cumulants. And fluctuations have the advantage, as I mentioned, that they are experimentally accessible and reliably computable in QCD. And these are like what I showed you before. It's like one in not so many plots in lattice QCD where you really have a direct comparison with heavy ion collision experiments. More generally, to get access to the freeze-out parameters, because so far we have only considered the Taylor expansion in mu b over t, one has to consider that the potentials are more. In particular, one can take mu s and mu q, where s stands for strangeness and q stands for charge. These are conserved quantum numbers. And if one has to set those chemical potentials as well in the simulation, one should better set them in a way that they reflect the thermal system that is created in the heavy ion collisions, in particular the net strangeness content and the net electric charge to baryon number ratios of the incident nuclei that are let collide. So most of the time, one has, for example, strangeness neutrality and a given relation that connects the density of charge and the density of baryon. Then one can write down P in a slightly more general expression than what you have seen previously on this set of slides, in particular in terms of all relevant potentials and of this, I hope, yes, now I can select it, that are the generalized susceptibilities. They are called generalized because, as you can see now, it is not just B for baryon, but also Q for charge and S for strangeness. And you have many of them because you have many combinations of powers in the series expansion. And the generic one can be written in this way. Okay, and then one can go ahead, measure this in a lattice calculation, and then compare with the cumulants of net charge fluctuations at freeze-out, which is what the experiments are able to extract according to this formula over here. Because in experiments, you can measure the yields of different species of particles, and then you get access to this. Okay, I have one last slide, which contains more results from Taylor expansion and analytic continuation, because as I said in the beginning, one of the things that you might want to look at is the bending down with temperature of the crossover region at high T and small mu. This as well you can write down in terms of a series expansion in powers of mu q over T. Now sticking back to the usual T versus mu q phase diagram and neglecting other kind of chemical potentials. And the relevant formula is what I wrote here on the slides. And only even powers of mu q appears, as in the partition function itself. You only have even powers because it is an even function of mu q and you have charge conjugation symmetry. All right, and then the C and 2, which are the coefficients, are observable dependent because the transition is not a real transition, but truly just a crossover. However, this feature of the phase diagram has been studied over many papers, and I'm just quoting 2 of them right here by looking at different observables in order to really get a complete picture of what is happening. And that is summarized in these plots, which all are just snapshots of the full phase diagram, where you can see nicely superimposed some experimental results for the freeze out and the corresponding lattice results for the location of this boundary based on the particular observables that have been picked in this paper that you can look at by clicking on the links, as usual. Okay, and yeah, apologies, I'm not covering something important about the Taylor expansion, namely the fact that people are trying to locate the critical endpoint by looking at the convergence radius of the Taylor expansion. One word of caution about that is that, as I said, there are infinitely many terms. So unless this converges very rapidly, and then you can get a good idea of the radius of convergence just by the first few coefficients, dividing the one against the other, or looking at something more sophisticated. In general, that's not clear. So results in that respect must be taken with a pinch of salt. And that's all I have also for this video, which happens to also be the last one. So I profit from this fact to say thank you for having watched the video, and I'm looking forward to the class and to your interesting questions. Bye-bye.